Hello, everyone. Can you hear me?
Yes, we can
Okay,
hear you.
so thank you. First of all, thank you very much for the invitation to give this presentation to share our work at our institute. Um, my name is Guillermo Gancio. I work at the Argentine Institute of Radio Astronomy. I'm the head of the observatory, and I'm going to share the work that we've been doing the last few years. As an introduction to our institute. Let me okay. Okay, a little bit of background. Our institute was created in 1962 in Buenos Aires, Argentina, by the CONICET. It was designed as a radio astronomical observatory for work on the H1 emission, in the hydrogen, the natural hydrogen emissions of the galaxy. We have two radio telescopes. The first was completed in 1966, and the second one was built by the end of the 70s. And both radio telescopes were used mainly for surveys of the sky to do complete maps of the southern sky in natural hydrogen, in continuum emission, and in polarization. You can see below there some pictures of the institute. Well, we are located in Argentina, near the city of Buenos Aires. And you can see down there our two radio telescopes. There are two single dish instruments of 30 meters in diameter each. So the first, as I mentioned before, the first scientific cycle was completed by the year 2000. It was intended for H1 surveys. By the year 2010, both instruments were not being used anymore. So in 2015, we started in a process to recover the observation facility of the institute. We tried to put into work again to be able to do some observations on with both antennas. So we start in the year 2015 with a very simple and a low-cost software-defined radio as a digital backend. And we were able to do the first observations of a pulsar. That kind of observation was never done before on our institute. And that took the attention of several researchers at our own institute. And we start to create a group for pulsar research, for pulsar observations and pulsar research. In 2017, we complete our a new backend with more uh, with more um, with more bandwidth. We achieve in the first stage 56 megahertz of bandwidth, which is very slow compared with other observatories, but it was our first step on going into this kind of digital instruments. And we also start a collaboration with the Center for Computational Relativity and Gravitation at the Rochester Institute of Technology with the Professor Carlos Fausto, who do this kind of pulsar research. That collaboration was called the PUMA collaboration for pulsar observing and monitoring. So at the moment, we are doing pulsar observations. Mainly, we are observing on a daily basis for the monitoring of several pulsars. As I mentioned before, we have two single dish radio telescopes of 30 meters in diameter with an equatorial mounting. The two antennas are operational now. The first antenna was put into operation in 2015, and the second antenna was put into operation in 2018. They both work at the L band with a central frequency of 1.4 gigahertz. The system temperature is roughly 100 Kelvin. They are low noise amplifiers at room temperature. And we have on each antenna 2 different sets of digital receivers covering between 56 and 112 megahertz of instantaneous bandwidth. So we are working with Pulsar Observations, and if you're not familiar on how we do the observation of pulsar, it's very interesting. It's very demanding on computational level, and basically what we want to do is we want to have spectrums in frequency. We want to have a lot of frequency channels, which is the I-axis there in the on the blue representation. But we also want to have these spectrums and these several channels very fast, because we want to measure very rapid changes of the pulsar emission on the start as it's rotating. So we want to have a lot of channels, let's say 2048 channels, and we want to have a very fast damp rate in the order of milliseconds to microseconds, right? So we have a very fast sampling rate and with a very high number of channels, and ideally with a very high bandwidth, which is represented in the plot. The plot shows a pulsar emission in the background, and the pulsar is being due to the dispersion measurements of the interstellar medium. The different channels in frequency came at different speeds, so the pulsar is being delayed. So that's why that's the reason why we need to have several frequency channels, so we can correct the dispersion measurement and we can recover the pulsar shape. So in order to do that, we have a digital backend, as before. It's based at the moment on commercial boards. These are boards from the Ethos company. And each of these boards that I'm showing there has a capability to have 56 megahertz of bandwidth. We have 2 boards for each antenna, so we can have 1 board on every polarization, so we can have both polarizations, or we can have 1 channel of 112 megahertz. At the moment, we have 128 frequency channels, and we are taking samples every 20 microseconds, and we have that connected with that scheme down there. And one of the important parts is the time synchronization between every board. We have a signal from a PPS, from a GPS, that gives a pulse per second signal, and we have also a 10 megahertz signal disciplinated by the GPS, so we can actually have a very good synchronization from every board, so we can recover in a proper way the pulsar shape, and so we can do also, which is the time of arrival measurements of the pulsar, which I'm showing here. This is a measurement of January 2019 of the pulsar vela, of the last glitch of the pulsar. And you can see that in this gray line here, the jump on the period of the pulsar. So in here you have the previous behavior of the pulsar with a very few measurements. And once we get the report of the glitch, of the jump in the period of the pulsar, we start to do a more complete monitoring, showing the new period of the pulsar. Another of the works that we are doing is the monitoring of millisecond pulsars. We are monitoring especially the pulsar J0437-4715, and we observe this pulsar on a daily basis. We've been observing from the year 2019. We did the first 1 year campaign, monitoring the pulsar and getting from those observations the time of arrival residuals, so we can monitor how the pulsar behaves uh, on this over a year, and we're continue monitoring this pulsar, and this observing campaign is also part of the gravitational wave detection campaign that we are trying to collaborate with the NanoGrav collaboration from the United States. So we can monitor the time of arrival of this kind of millisecond pulsars in order to, in a long-term observations of several more years, see if we can make a detection of the gravitational wave. This project is, as I mentioned before, is realized by the NanoGrav collaboration by the US, and there are several institutions around the globe doing these kinds of observation and collaborating with them. As a result of this campaign of between the year 2000 and 2020, we did an extensive monitoring of this pulsar J04, which I'm showing here. There is, well, different, along the year we have different sets and different profiles of the same pulsar, so we can see how the pulsar shapes has been evolving during the year and during our observations, with different configurations and different sets of beams that we use to process all the observations. So we reprocess all the observations with different configurations, and we find what are the best for the best profiles that fit the best for this kind of observations. So, like a summary, we recover the facility, the observing facility of the institute that I work. We recovered 2 radio telescopes, and we prepare them to make specific pulsar observations. Now we're extending this pulsar for timing analysis for glitches observations, and we are moving forward to the measurement of FRBs. We are also working on campaigns to observing magnetars in a regular basis, and we are also doing different kind of continuous observations of blazars and other and similar objects in the southern sky. And we're working also on the next generations of backends to be implemented on our institute. We're basing our work on the Casper collaboration, which is a collaboration for digital backend design. We have a Roach board, which is in the commissioning stage. We received this board from a collaboration with the University of Mexico. We did the software for it, and we're on the testing stage for the release of the board for the observations. We are designing new receivers for our antennas, so we can move from 100 megahertz bandwidth to almost 1 gigahertz of bandwidth with 2 polarizations. We are also doing a deployment on RF over fiber, so we can have all the RF directly on our control room, and that makes easier to do all the process and all the frequency shifts to the digital converters and to the digital backends. And we want to increase the instantaneous bandwidth from 100 megahertz that we have now to 500 megahertz on both radio telescopes. So we can increase our sensitivity, and we can increase our current observing capabilities. So that's it. Thank you very much. And if you have any question, please